So in this lecture, I wanted to use our past knowledge from previous lectures where we understood that light is a wave to explain what colors are, what it really means to be a color. Let's say I have an electron here, and I start wiggling it up and down at a certain speed. That will launch a wave into space that also moves up and down at a certain speed that will travel through space, in this case to the right. And let's put out an electron here that isn't moving beforehand. And when the wave hits this electron, it starts wiggling up and down at the same speed that the original electron was wiggling. This wave in between that caused this electron to eventually wiggle is what we call light. This wave here, causing the electron to bob up and down. The speed at which these electrons are moving changes the speed at which this light wave moves up and down, as well as the distance between peaks, or the wavelength. This is what we call the wavelength. And that speed at which we move these electrons up and down is what color really means. If I wiggle it faster, if I wiggle this electron here faster, it sees, effectively, a different color than if I wiggle it slower. To make it more concrete, let's say that this electron here is in the back of your eye. This is exactly what's going on right now. This is a very poorly drawn eye. This is the front lens of your eye called the cornea. This electron back here right now is seeing the yellow light at this point, which means the electron in the back of your eye is wiggling up and down at a certain speed. And the light that is producing that is moving up and down at a certain speed as well, and has a certain wavelength to it. So now that we have that idea out in the open, let's go ahead and give specific examples. I'm going to wiggle the electron out here to produce light to enter your eye at a very slow speed, which makes a very long wavelength. And we'll call this wavelength 760. Now, let's go all the way down here and wiggle the electron exactly twice as fast. That's about twice as fast. Which will produce a wavelength that is exactly half the wavelength of the red wave up here. Half of that wavelength would be 380. This is exactly the wavelength and speed that I need to wiggle the electron above to produce red light for you to see it. It means that I have to wiggle the electron at 394 trillion times per second, or 394 trillion wiggles per second, which produces a wavelength that's not quite 760. It's 760 nanometers, which is a billionth of a meter. Likewise down here, because I had to wiggle this twice as fast, I get 789 trillion wiggles per second, which produces a light wave at 380 nanometers. This is the highest frequency light that we can see, the shortest wavelength light. And this is violet. So right now, there are light waves coming out of the screen with this particular color that have a wavelength of 380 nanometers that are hitting the back of your eye, causing electrons to wiggle very, 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 very fast. And that subsequently, the light at the top of the screen that is producing red light is wiggling half that speed in order to produce wiggle movement in the electrons in your eye that are wiggling half as fast as the violet light. The speed at which the electrons wiggle in the back of your eye is color. Let's go ahead and do more more colors so you can get a feel for what it is that your eyes are actually seeing. It looks like my artwork is not failing me, except the violet light is a bit too stretched out. Let me go ahead and fix that. Violet light has the shortest wavelength. There we go. Now, note, because I'm a bad drawer, that these waves all have a different amplitude. They have a different distance between the peak and the trough. That is not what color is. That's how intense the light is. If it's very, very bright, then the wave is very, very big. If the wave is small, then it's very faint and it's very difficult to see. That's not color. Color is just the distance between the peaks, how fast it's moving up and down. So this is yellow light at a wavelength of 620 nanometers. Blue light has a wavelength of 550 nanometers. Did I just say blue light? I meant green light. And here, blue light at 420 nanometers. This is the entire range of wavelengths and colors that we can see. There are clearly more wavelengths in between these colors that I haven't drawn. Notice I haven't drawn orange, but it's somewhere between red and yellow, which means its wavelength is probably somewhere around 700 nanometers. But this is the entire range of what we can see. If electrons wiggle faster than this and produce light that moves up and down faster than this, say 300 nanometer wavelength, then we actually get light that is ultraviolet, above violet. This means above violet, so above that frequency. Our eyes, electrons, can't wiggle this fast, so we don't see it. The light passes straight through. It's invisible to us. Subsequently, if we had light all the way up at, say, 900 nanometers, which oscillates at a slower rate, this is probably something like 320 trillion wiggles per second, something like that. This is below the frequency of red, which means it's infrared color. Infrared, below red. This is also wiggling too slow, so we can't see that. We cannot see anything below red, and we cannot see anything above violet. So this is the spectrum of visible light. This here is the visible spectrum of light. And it is no coincidence that this frequency here is exactly twice that of this wave here. We actually call that an octave, because if you take this frequency and multiply it exactly by 2, you have moved the wave an octave away. In sound, if a sound wave is vibrating at a certain pitch, that's what your ear hears. Sound pitch is basically ear color, you could say. Then if you doubled that pitch, you would move up in an octave in music. Well, here we actually say the same thing. This is an entire octave of light. And this octave of light actually gives the most information out of the entire spectrum of what materials do. And that's pretty much the reason why we see it and don't really see everything else. Being able to see more colors wouldn't really tell us much more about the universe. It would tell us a little bit, but not nearly as much as the colors that we currently see. So there you have it. This is the visible spectrum of light, and electrons wiggling up and down at certain speeds generate colors.